able to write or calculate the de Broglie wavelength of alpha particle, beta particle, or deuterium nucleus, etc. You can actually calculate, and you can also find the ratio of them if potential is given, kinetic energy is given, etc. Okay, so kindly watch through the entire length of the video. It's going to be a useful one, and let's start from the basic thing. So de Broglie wavelength of a particle moving with momentum is given as lambda is equal to h by p. So in our +1 grade, we know that momentum is the product of mass and velocity, and kinetic energy is half mv square. So in this kinetic energy, if I multiply and divide by m, so I'll be getting half m square v square by m. But mv is momentum, m square v square is square of the momentum, so it becomes p square by 2m. So p square by 2m is kinetic energy, means p square is equal to 2m into kinetic energy, and the momentum p equal to square root of 2m into kinetic energy. So based on this, you can write the de Broglie wavelength, if you know the kinetic energy of the particle, is root h by root over 2m into kinetic energy. So you can use this in various type of problems. Suppose if alpha particle and proton, they both have equal kinetic energies. So kinetic energy of the alpha particle is equal to kinetic energy of the proton. What is the ratio of their de Broglie wavelength? De Broglie wavelength of alpha particle is h divided by root of 2 into mass of the alpha particle, kinetic energy of the alpha particle. De Broglie wavelength of proton is h by root of 2 into mass of the proton, kinetic energy of the proton. Just divide these two equations. You know that lambda alpha by lambda proton equal to, and this comes to the denominator, this comes to the numerator, so it's rest of the things will be cancelled. When you divide these two will be cancelled, 2 will be cancelled. Since kinetic energy of the alpha particle is equal to kinetic energy of the proton, these two will be cancelled, so you will be getting square root of mass of the proton by mass of the alpha particle. So we know that an alpha particle is the helium nucleus, so 2 protons and 2 neutrons will be there, and whereas proton is only one. Suppose if its mass is m, mass of the alpha particle compared to this is 4 times m. So this we are writing it as m divided by 4m, so that is 1 by 2. Okay, so lambda of the alpha particle, lambda of the proton equal to 1 by 2 when they both have kinetic energies. Suppose if they ask the opposite ratio, lambda proton to lambda alpha particle, it is equal to 2:1. This is one useful way of writing this. The other part of this is, we know that in our 11th standard, the amount of work done is the kinetic energy acquired, that is K final minus K initial. Sometimes if the initial kinetic energy is 0, the amount of work done is directly equal, will be equal to the amount of kinetic energy acquired. But in 12th standard, we also know work done per unit charge is equal to potential difference, which means that work done is equal to charge into potential difference, and work done is actually equal to kinetic energy. So kinetic energy is equal to charge into potential difference. When you substitute the same here, we will get the lambda of the particle equal to h by square root of 2m into charge into potential difference. So if you know this, suppose if they say an alpha particle and a proton, an alpha particle and a proton both are accelerated by the same potential difference, what is the ratio of their wavelengths? So lambda equal to h divided by root of 2 into mass of the alpha particle, charge of the alpha particle into potential difference, and lambda of the proton equal to h divided by square root of 2 into mass of the proton, charge of the proton, and potential across which it is accelerated. When you divide these two equations, the common terms will be cancelled, like h and h will be cancelled, both are accelerated by the same potential, cancel, 2 and 2 will be cancelled. So as a result, what you get here is lambda alpha particle. I will write this over here so we can further proceed this. So here lambda alpha particle by lambda proton equal to, this goes to the denominator, this comes to the numerator, equal to root of mass of the proton, charge of the proton by square root of mass of the alpha particle, charge of the alpha particle. So you can say in one shot, mass of the proton, charge of the proton by mass of the alpha particle, charge of the alpha particle. We know that mass of the proton is m, means mass of the alpha particle is 4m. We just discussed it over here. See, 2 proton, 2 neutron combined to form alpha particle, whereas this is only 1 proton. So if it is m, this is 4m. But here proton has 1 electronic charge, whereas alpha particle has proton and proton, so 2 times electronic charge. Hence charge of the proton is E, means charge of the alpha particle is 2e. So cancelling the common term, m and m will be cancelled, e and e will be cancelled. So it is equal to 1 by square root of 8 or 1 by 2 root 2. So when alpha particle and proton, they both are accelerated by same potential difference. So lambda alpha particle by lambda proton is 1 by 2 root 2, and lambda proton by lambda alpha particle is 2 root 2 by 1. So right now we have we have done two parts of the formula. So for your reference, I'll just write that up again. So lambda equal to h by p is the de Broglie wavelength. So which can be written as h by root over 2m into kinetic energy, which can also be written as h by root over 2m charge of the particle into potential across which it is accelerated. In the followed video, we'll see what we can do about the kinetic energy for a free neutron or something, and then we do the same for an electron also. Okay.